Hi everybody, this is Dr. Schultz, and we are going to do a quick lesson on the physics of the simple pendulum. Yesterday in class, we made some experimental measurements on a simple pendulum. We took a mass and we tied it to the end of a string, and we let the mass swing back and forth under the influence of gravity. So the picture would be something like this. You have a mass m, and it's tied to the end of a string that has a certain length, L. And that string makes an angle that we're going to call it theta in this picture. And of course that angle changes as time goes by because the mass swings back and forth. Okay. Now this is called a simple pendulum because all of the mass is found at the very end of the pendulum, in that ball at the end. And we really neglect the mass of the string. We say that the mass of the string is practically nothing compared to what's at the end. So just so that you know, a simple pendulum is one where all of the mass is at the end. Now, one of the things that we discovered yesterday with this was that the period of this simple pendulum does not depend on the amplitude. That is, how far you pull this thing sideways. And that kind of suggests that the simple pendulum might follow simple harmonic motion. Okay. So that's what we want to explore here, and we want to show that it does. So I guess we could say that if the pendulum obeys simple harmonic motion, then what? Well, then there should be some type of a restoring force on that mass, and that restoring force should follow Hooke's law. So if we look at that picture, I think the idea would be that there should be a restoring force that's going to be pulling the mass back towards that dashed line. And that force that pulls the mass to the left should be directly proportional to the distance of the mass from that line. So it's a lot like a spring. So I guess to finish our sentence here, if the pendulum obeys simple harmonic motion, then the restoring force should be directly proportional to theta. Right? Because the bigger the angle, the stronger the force should be. And that kind of is what guarantees the fact that the pendulum keeps the same period no matter how far you pull it back. Because if you pull it really far, the force should be that much stronger. Okay. So that's the idea. Now, when we say the restoring is directly proportional to theta, it also, we could say, and also to x, meaning the kind of that horizontal displacement. Okay. And that's what you guys measured in the lab today, is you measured the sideways distance with the ruler. So kind of by trigonometry, x and theta should kind of go together. And in math class, I guess you learned that x is equal to, L theta. They should be related somehow. Okay, so a little bit more on that later. So, but we would expect that the bigger that x is, the greater the restoring force should be in the opposite direction. So the way we'll do this is we'll show it. Is we're going to draw a free body diagram for the mass, and then we'll look at what the diagram tells us, and we'll see if we can come up with a restoring force. So let's the force act on the mass. And so at this instant, the mass is over here. Of course, we have weight. That's mg, and that's a constant force. Also, we have a tension that acts on the mass, and that tension force is going to act in the direction of the string. The string is pulling on this object. Okay. And that's it. Those are the only forces that you have, just those two things. We don't worry about friction or air resistance or anything like that. Now, what I'm going to do is now I'm going to redraw the mass right here, because this first picture was getting kind of crowded. And I'm going to tilt my coordinate system, and I'm going to line up and have an axis that goes along the string direction. So this is an axis here, and it lines up with my string direction. And then I'm going to have an axis which is perpendicular, so kind of like an x and a y axis. Now, in this picture, my weight vector kind of falls like this. And the reason that I'm going to tilt my x and my y axes is because I know that the string doesn't stretch at all, and the tension that the string is pulling with has to perfectly cancel out this component of the weight. Yeah, so we're actually taking the weight vector, which goes straight down, and we're finding its projection along the direction of the string, okay? Because these two forces need to cancel each other perfectly, okay? They have to in our tilted system here. So let's call this tilted axis. This is going to be our y-axis here. And our x-axis can go this way. So in the y direction, the forces, they have to cancel, okay? And that's something that we can totally count on. Now, one thing that you'll need to know in order to figure out what this force is here is you'd have to say, well, is this theta or is that theta? And I hope you can see that this angle and this angle are basically the same. So this is your theta right here. And that means that this force, this component, is going to be mg cosine theta. Okay? So what does that get us? Well, it says if you take the sum of the forces in the y direction, they are equal to 0. And we have tension going up, and we have mg cos theta going down. And they have to cancel, so that means that the tension would be equal to mg cos theta. And in fact, if you keep the angle very small, so for small theta, meaning less than 15 degrees, about less than 15 degrees, the cosine is approximately equal to 1. All right? So for really small angles, the cosine is going to be close to 1. So basically the tension, I'm going to put a wiggly sign here, the tension is pretty much equal to the weight of the object. That's an approximation, right? The cosine of theta isn't exactly equal to 1, you know, unless the angle is 0. But if the angle is close to 0, the cosine is very close to 1. You can try that on your calculators. So anyway, that's kind of a neat little result. It doesn't show us that it's Hooke's law, but it tells us that the tension in the string is pretty much equal to the weight. Now, what if we look at the sum of the forces in the x direction? Okay, and here's kind of where we want to be on the lookout. Okay, because there's going to be some type of a restoring force that happens here. And so I'm going to go back to my diagram, and I'm now going to complete this box. And I find that I have an unbalanced component of the weight. Unbalanced, and it's equal to mg sine of theta. And that's the only force that acts in that direction. So that's what we have, is the mg sine theta. So I'm going to write that down. That's mg sine theta. That's equal to my restoring force, Fr. Okay. I made a little bit of a mistake here. I'm going to correct it though right now. I noticed that my x direction is going to the left here. This is actually the negative x direction, so this should be a negative here. That's important because the mass is on the positive side of the equilibrium. It has a plus x position, and the direction of this force is in the negative x direction. So that's pretty important to have that negative sign here, here. Okay, so this is the positive x direction. Okay. So so the question is if you look at this now, you say, okay, well, here's a restoring force. Is that restoring force following Hooke's law? And technically, no, it is not, because the restoring force changes with theta in a sine way. And a sine function is not a linear function. So technically, theoretically, the pendulum does not follow simple harmonic motion. It doesn't follow Hooke's law. However, for small theta, again meaning less than 15 degrees, the sine of an angle in radians is equal to the angle in radians. And this is something that hopefully you've learned in math class. You can check it on your calculators. You know, come up with a small angle, put it into radians, take the sine, and you will get that angle back. It will be really close. And this is an approximation. I'm going to put a little wiggly sign there. It's not exactly equal, but it's really pretty close. And that works. That's a trick that works for angles that are less than 15 degrees. This is called the small angle approximation. I would highly encourage you to check this on your calculators. You know, take 10 degrees in degrees, convert it into radians, and then take the sine of that angle, and it should be equal to the angle itself in radians. So it's a good thing to check out. So what that means is that we can actually kind of say here that the restoring force is approximately equal to the weight of the object, which is constant, times the angular displacement from equilibrium. And this is Hooke's law. Okay, written this way, that is Hookean, right? Because it's like, you know, for a spring, the restoring force is equal to negative k times x. Well, here for a pendulum, it's equal to negative weight times an angle. So this is very Hookean, right? If we use that small angle approximation. So that's significant. Now, the last thing we'll do here with this is let's go a little bit further and see if we can make this even better. I'm going to do a substitution. I think I'm going to use a different page here. So I had negative mg times theta in radians is the restoring force. So I'm just copying that down. Now, if I look back on my original picture, theta in radians is going to be equal to x over L. Okay. Right. So that's an arc length, really. Right. That x would be like an arc length, but it's practically a horizontal line segment. Okay. So for a very small theta, this is just going to be a tiny little distance compared to the length. And we can say that the arc length, or the length of this, is equal to the ratio of x divided by L. Okay. When I write it that way, I can group my constant terms together. And now I really can see Hooke's law. I hope you can see it. Okay. This is very much like Hooke's law, because Hooke's law for a spring was that. Hooke's law for the pendulum is that. And so basically for a pendulum, K is going to be equal to mass times gravity over length. It's the weight divided by the length. Okay. So K isn't a spring. This is not a spring. But that. So now you really see it, I hope, that the pendulum is following something like Hooke's law. And so this is, the further you pull the pendulum back, the harder that force pulls back in a linear sort of a way. It gets even better than that, because you can actually kind of like reuse some of our results from before. Remember for the spring, we found that the period was 2 pi times m over k. Well, that was for a spring, right? But let's substitute in k for the pendulum. That would be 2 pi times the square root of m over mg over L. Now, before I do anything else, something really cool happens. The mass cancels out, and that explains why in your lab yesterday the mass did not matter, right? So I'm hearing everyone going, oh, I hope. But for the spring, the mass didn't cancel out because the spring force doesn't know about the mass of the object. But in the case of gravity, the pull of gravity is proportional to that mass. So that's why the mass cancels out. And then you're left with 2 pi times L over G. And that is the kind of end result, which tells you the period of a pendulum in terms of its some fundamental parameters here. So if you're going to make a clock out of a parameter, out of a pendulum, there's really only one parameter that you can tweak, and that would be the length, right? Because gravity, you're stuck with it. You can't do anything about that. But the length you can change. And now I hope you can see that the period should be proportional to the square root of the length if you graphed it. All right, so hint, hint. This is might be a good way to straighten the graph from yesterday's activity. But just to make that point, that's something that you can do. The other thing is if you look at G, if you were to take a pendulum to a different planet, the pendulum would keep different time. Going to a planet that has bigger G, like Jupiter, something that has very strong gravity, would cause the period to be shorter. And I hope that makes sense to you because a stronger gravitational pull is going to restore the pendulum back to equilibrium that much faster. So in practice on Earth, we don't really change G, but the length is something that you can change pretty easily. Okay. All right, so that would be that. So hints, if you wanted to straighten graphs, how would you straighten the graph? Well, we start off with length being independent, period being dependent. If I want to straighten that graph, I could have a few options here. I could plot the square root of the length versus the period. I could also plot the length versus, hopefully you're thinking it, t squared. And both of those graphs should give me kind of a linear shape. Okay, so I do want you to do that in class today, is I'd like you pick a way to do it and graph it up. Personally, I think this is a little bit easier. I like squaring things better than square rooting them. So I guess I would recommend doing it this way if you can, is to graph it that way. And what I want you to do is get that graph, maybe do period squared versus L, and then you look at the slope and you verify that the slope is consistent with this formula that's up here. Okay, so that's something that you can do there. All right, so we're gonna kind of leave it at that. You've got a little bit of stuff to do here with your labs. And there was one more thing I was going to show you. Yes, of course. Actually, Andreas, one more thing. This is to generalize. Oh boy, generalize. SHM. A good way to generalize SHM is to look at the differential equation that we talked about a few days ago, and to recognize that all simple harmonic motion is going to basically obey that differential equation. Okay, all simple harmonic motion. If it's a spring and a mass, you've got a spring constant and a mass. If it's a pendulum, you're going to have the modified spring constant, right? And then you divide out the mass, and so that modifies a little bit. But all simple harmonic motion kind of follows this general formula. A lot of times you'll see this written, especially if you take more physics or engineering. Instead of writing k over m, this will be written as omega squared. And you just have to remember that omega is the square root of k over m. Okay, that was something that we showed several days ago. So you really need to be able to recognize these equations as being the equations for simple harmonic motion. You really have to know that omega is related to the constant in the mass through the square root function. That's very pops up a lot, and if you've been doing your homework this week, you'll see that this comes up quite a bit too. So this is one of those things where you really want to memorize it and know it so that you can respond quickly to questions about those three things. So okay, I'm going to stop now, and I think what I'd like everyone to do is to work on graphing the data from yesterday in your lab journals. I think there should be some graph paper in the room if you need it. Otherwise, you can use your lab journals. I'd also like you to write up something at the end that kind of explains, your results and how your predictions were supported or not, and what you learned from this. So kind of finish up just writing that in your journals. That would be good. And I think the sub will explain what to do after that. Okay, thanks.